Most assume that as you shrink a model through quantization, quality degrades smoothly and linearly. Half the size, half the intelligence. But plot actual retained quality against bit depth, and the curve looks entirely different. A completely flat plateau, followed by a violent vertical cliff. That flat section represents the near lossless band. Compressing a model from 16-bit precision down to 4-bit costs almost nothing in measurable capability. You can get all that memory savings practically for free. But the moment you drop below 4 bits, uniform quantization structurally breaks the network. This mock terminal shows exactly why that break is so dangerous. The model doesn't crash or start spitting out obvious gibberish. It generates a grammatically perfect, highly readable paragraph right before confidently delivering a hallucinated math proof and malformed JSON. The model maintains its conversational tone long after its capacity for logic has collapsed. Since Fluency survives the cliff, evaluating a heavily quantized model on how well it writes emails guarantees deploying a lobotomized system to production. To understand why this happens, we have to look at the mechanics of rounding. This continuous line represents a high-precision 16-bit weight. Quantization forces that value to snap to a rigid, discrete step. That tiny red delta is the quantization error. In isolation, rounding a single weight to a slightly coarser value is mathematically harmless, but a transformer architecture acts as an unforgiving error multiplier. As the signal passes through the deep stack of layers, those small red deltas begin to compound. Each layer outputs a slightly corrupted signal, which immediately becomes the baseline input for the subsequent layer. Multiply that compounding effect across millions of weights and dozens of layers, and the final output signal is drowning in noise. The earliest and most sensitive indicator of this architectural noise is perplexity, the model's statistical uncertainty about the very next token. Yet practitioners rarely look at perplexity, relying instead on top-1 accuracy, a metric that is historically one of the very last things to register the structural damage. Top-1 accuracy artificially inflates the model's health score because it only rewards getting the single most likely token right. It completely ignores the collapse of complex sequencing happening right behind it. Trusting a reassuring top-1 score is a trap. It is the metric least sensitive to the compounding mechanical failure tearing through the network. This compounding error degrades the model in a strict, predictable order. This stack illustrates the hierarchy of fragility, showing exactly which capabilities fail first. Math and multi-step logic sit at the absolute bottom of the threshold. They are the first casualties. Multi-step reasoning relies on highly precise intermediate values. Coarse rounding derails those specific values, breaking the logical chain. Code and structured output like JSON fail immediately after. Generating syntax is unforgiving. A single perturbed token resulting in a dropped closing bracket completely invalidates the output. Long context recall degrades next, as attention errors compound severely across extended sequences. Instruction following erodes shortly after, particularly the model's ability to honor negative constraints. But casual chat remains structurally intact. It is highly resilient, capable of producing grammatically plausible text despite overwhelming parameter noise. Testing a quantized model by having a casual conversation with it tests only its most robust feature. It entirely masks the catastrophic loss of the model's load-bearing cognitive skills. To understand this failure, we must look at exactly where the physical network breaks under uniform quantization. We have to dive into the dense architecture itself. Below 4 bits, uniform quantization applies the exact same coarse precision to every single parameter, ignoring the fact that a tiny fraction of those weights do the vast majority of the work. We can highlight those critical choke points on this architectural wireframe. The bright, sparse dots are outlier weights, a tiny minority of parameters carrying disproportionate magnitude. The horizontal bands represent attention layers and input-output embeddings. Errors introduced here instantly corrupt sequence propagation and the integrity of the data entering and exiting the network. In modern frontier models, the central node cluster, the mixture of experts router, is the ultimate vulnerability. When you subject that router to uniform low-bit quantization, it starts misdirecting the signal. Tokens are shunted down the wrong architectural paths, completely bypassing the specialized expert knowledge they were supposed to access. Blindly applying a uniform budget below 4 bits crushes these precise choke points. You get a model with an appealingly small memory footprint that is entirely useless for complex work. There is an engineering alternative to the uniform sub-4-bit cliff. It requires shifting to mixed precision dynamic quantization. This comparison highlights Unsloth's calibrated dynamic builds of the Kimi K3 model. On the left, a naive uniform 2-bit model. On the right, the dynamic build data points. The uniform build is practically unusable. The dynamic build, using the exact same bit budget, maintains a survivable 90% accuracy. Push that dynamic build down to an extreme 1-bit budget, and it still retains nearly 80% accuracy. This works by selectively protecting the choke points we just identified. The vast majority of the network is dropped to a 1-bit or 2-bit resolution to meet the memory budget, but the highly sensitive outlier weights, attention layers, and routers are upcast to a protected 8-bit precision. By mathematically measuring the damage and protecting the minority of load-bearing weights, intelligent bit allocation bends that catastrophic cliff back into a survivable slope. This split screen shows what happens in production when you push a uniform model off that cliff. You will see degenerate sampling emerge as repetition loops, where the model gets stuck emitting the exact same token endlessly. You will see format collapse, where the unforgiving nature of structured output results in dropped tags and malformed tool calls. And worst of all, you will see confident hallucinations, where the model asserts objectively wrong answers using a perfectly fluent register. These qualitative structural failures are completely invisible to a single aggregate score on a public leaderboard. Never trust a reassuring top 1 score to guarantee structural integrity. The only valid evaluation is running the model against your specific reasoning chains, JSON schemas, and retrieval tasks to find the lowest bit depth that perfectly executes your work.